for solving a real robotics task. And right now I'm going to show you just preliminary work, but it's still encouraging. So here is a baseline. Here's what happens when you just try to directly do the transfer learning from sim to real without doing anything special. It's kind of shaking. Oh, it succeeded. So that's good. So it really kind of, it's not able to understand where the mistakes are coming from. And so it does these undesirable behaviors. It is unable to push this hockey puck to the desired destination. But if you train with this randomization, then it's just better. So here it succeeds. And you can see that it's very clearly adaptive. It corrects itself. And it's just not particularly, like the fact that it's running on a real robot rather than a simulator, this doesn't seem to pose it a particular challenge. No, that's not this version. But yeah, so that's I think that's pretty cool. So I want to talk about another work on another result on meta-learning, another very simple thing you could do with meta-learning, which is, well, can you use meta-learning to learn a hierarchy, to learn an action hierarchy? Hierarchical reinforcement learning is one of those really good ideas that don't work yet in reinforcement learning. If you have an action hierarchy, you get a number of really great benefits. You get the ability to deal with very long time horizons and with really good credit assignment. And also your exploration is much more directed, because when you say, I'm going to choose a high-level action, I'm going to go to the store. So now going to the store in a pretty directed way. I think the first hierarchical reinforcement learning paper was done by Jeff on the feudal RL from 1995. But it doesn't, hierarchical reinforcement learning doesn't work even today. But what I want to show is that in the meta-learning context, it is very easy to learn an action hierarchy. Think about it. If you have a distribution over tasks, and you specify your optimization problem as one of, can I please find low-level actions that make it possible to learn new tasks from my task distribution as fast as possible? So here is the system. You say, I've got my policies, I've got my low-level actions and their neural nets. I'm going to treat them as low-level actions. I'm going to give them to some other learner. And I'm going to do a short run of reinforcement learning with this new learner, where it can only use these high-level actions. You run it for a little bit, and then look at the performance of your reinforcement learning. So you run your reinforcement learner for 5 minutes. You give it 5 minutes. You run it for 5 minutes, you got some results. And then you say, OK, I would like to change my low-level actions so that when I run it next time, it's going to be a little bit faster. So you backpropagate through the entire training loop of the reinforcement learning algorithm all the way down through the low-level actions. And I want to show you a video of how it actually behaves in a toy setting. And so after training, you have this little ant which is crawling, and it has only 3 sub-policies. And once it has these 3 sub-policies, it is able to learn to solve tasks like this one pretty quickly, because the sub-policies are good. It has, a sub-policy of go forward for 500 steps, or go left for 500 steps. So in this case, it only had 10 sub-policy selection. And so it succeeded. So you just say, my goal is to learn low-level actions, which make it possible for reinforcement, for a quick run of reinforcement learning to succeed as much as possible. So that's it. It's a really simple idea. And then you just compute your gradient estimate, scale it up a little bit, and you can learn these low-level actions. Now, of course, all these approaches to meta-learning have a limitation, that they require you to specify a distribution of the tasks. Okay. And I think that actually this is the biggest problem with the popular approach to learning, the non-neural architecture search, that you have the same limitations of supervised learning, where if you say, I have a distribution of the tasks, so my training distribution of the tasks must be equal to my test distribution of the tasks. And I think that this condition is almost always false. I think it is very rare to find a situation where the training distribution over tasks is equal to the test distribution of the tasks. And so it will be pretty desirable to develop some kind of learning algorithms which will be successful even when your test case is a little bit outside of distribution. Because if you think of your supervised learning contract, when you do supervised learning, you have a contract with the model. The model says that it promises to give you the right answer as long as the data comes from the correct data distribution, the training data distribution, which is equal to the test data distribution. Under this condition, the model will succeed. But should your test case be out of distribution, even in one aspect, so let's say it's like almost exactly in distribution, but there is this one way in which it is out of distribution, then the model has permission, according to the contract that you made with it, to give an arbitrarily bad answer. And adversarial examples are a great instance of that, where you say, okay, it's basically the same thing, I'm just going to perturb it a little bit, and now the model is hopelessly lost. And it just seems so counterintuitive that humans, that this should be the case, because humans seem to be a lot more immune. Although it turns out that if you flash a light into a person's eye in a way that's very correlated with their EEG, then you can induce a seizure. So maybe that's an adversarial example for humans. But it's definitely, it really seems unlikely. Humans really don't seem to be susceptible to, like, I take my image and I just give it a small perturbation. It's the same thing. I don't think there is any human that will be confused by that, at least, given it's my current belief as of December 2017. So anyway, my point here is that if we solve the problem of generalizing a little bit out of distribution, I think meta-learning will work a lot better. Okay, so now I'm going to the last part of the talk, which is self-play. And I think self-play is the coolest thing ever, and it became a lot more popular over the past few weeks because of AlphaZero. And I just want to highlight this one result of self-play from 1992 by Jerry DeSauro, which looks, if you were to, so I don't know if you can see the figure, but he has like different plots that show the performance of different neural nets with 10 hidden units, 20 hidden units, 40 hidden units, and 80 hidden units. And now, if you had 2 more zeros or 3 more zeros, that would be basically a 2017 paper. What he did is that he said, okay, he will use Q-learning, he will use a neural network to represent a policy which is trained with Q-learning with self-play to defeat all humans in backgammon. And not only the neural network defeated all humans with backgammon from no expert knowledge about the game, but it was able to discover new moves that went counter to the conventional wisdom in backgammon. 92. And basically what happened after this is that, I mean, those were the sad times when computers were slow. And so it was kind of lucky that backgammon was a game so easy that you could solve it with a network with only 80 neurons. You know, makes you wonder what are we doing with all our neurons? But it actually happened. And it's just unbelievable how modern this paper is, even though it's so old. Now, of course, self-play has also shown itself in AlphaGo 0 and later in Alpha 0. You just scale it up a lot, improve your URL, and great things happened. We've also seen self-play work well in Dota, which was our result from OpenAI, where we beat the world champion in the 1v1 version of the game. Again, massively scaled self-play. And I want to talk about some of the reasons why I'm excited about self-play. So, like if you think about, if you look forward and you say, okay, not only you say, I want to train agents which can solve truly wide variety of tasks. I want to train an agent which can then accomplish very difficult goals in the human world. Like what are we going to train this agent on? It's not self-evident. The answer is not self-evident. But I think there is one answer which looks at least plausible today. And I think the answer is the competitive multi-agent environment. You put your 100 agents into a simulated world, and you give them conflicting objectives. And the world needs to be sufficiently open-ended. And so what's going to happen is that as the agents become smarter, as each agent gets smarter, all the agents will become smarter. And so the society of agents that will be created will always pose a challenge to its members. Just like in the human world, the reason humans find life difficult is because of the other humans. And so if you look at the world without humans, then you don't, a squirrel can do just fine in a world with there are no, a squirrel needs to deal with other squirrels, but there is no need for a big brain if there are no other entities in the world with a big brain. And so I just want to highlight one result from 1994 by Carl Sims. And I actually strongly recommend watching, he has a video on YouTube. So just search for Carl Sims Artificial Life, where he has basically tried to do that. He said, okay, I'm going to take the best computers of 1994, this 33 megahertz, 386, and I'm going to try to evolve artificial life. So he tried to evolve both the neural net controller and the morphology. And he gave them all kinds of little tasks to compete against so that they would have an incentive to improve. And he got really cool, beautiful results. And I think everyone should watch it. This was, artificial life was one other direction that everyone deemed is unworthy. But it's because of the sad times of slow computers, which are now beginning to end. We are just at the cusp of the real compute tsunami. Oh, actually, I have the video. You know what? If I have enough time, I'll show you the video of Carl Sims. Now I want to show you what we did. He said, okay, Carl Sims stuff looks really cool. Can we do something similar? Where you say, okay, you try to create a self-play environment in a simulated physical world, where here you have a sumo game. You have a game of sumo. You're trying, one of the agents trying to push the other agent outside. And you see, they're pretty good balance. You see how the red humanoid ducked. It jumped to the side. And they look like little ducks. And so you can see how self-play, when done right, gives rise to this potentially unbounded complexity. And I think the challenge there is very similar to how neural nets have been back in the day, where you need to set it just right. If your scale of your initialization is wrong, it's not going to work. And so I think the same is here. Yeah, if you do it wrong, it's not going to work, but there is a way to do it right. And we know that there is a way to do it right because it's not unrelated to evolution. So yeah, you can see the soccer here. They learn to kick. Is it going to block? No, it didn't block. Okay, so see, the goalie is doing the right thing, and he was able to block. Good move. Oh, this is really cool too. Look at this. Look at how it's. Okay, so now it ducked under his hand. And this is an example of the skill transfer, where you say, okay, take the sumo agent and apply big random forces on it, what's going to happen? Is it going to keep its balance? And the answer is yes. And so kind of what's really needed for this line of research to really become self-sustaining is for agents which are trained in this kind of an environment to do something useful outside of it. Because ultimately we don't care about agents in a simulated world competing for some artificial resource. But we do care about agents doing our homework and cooking our food. And so what I was actually hoping to do here is that, okay, we train these agents in simulation, and then we'd fine-tune them on some useful simulated robotics task and see if it will be much easier. So that's turned out to be not so trivial to do. But I think that's what needs to happen. You have this big multi-agent world where the agents have this general competency, and then you specialize them to something that we actually need. And so I want to show one more slide. Yeah, so designing this environment is a challenge. But you can at least see how, in principle, if you were to ride the compute, if you were to surf the compute tsunami that's approaching, this approach could go pretty far. And it connects very nicely with meta-learning, because in meta-learning you need to have this great big variety of tasks. And I think here, the agents, as they try to compete for the limited resources, will cause a great deal of different challenges to each other. I also want to talk a little bit about one peculiar characteristic of these self-play systems. These self-play systems are different from supervised learning because they let us convert compute into data. If you want more data for your self-play system, you just put more compute in, and the agents get more experience. And the more compute you put into it, the higher quality the data is, the faster they learn. So one thing that's interesting about our experience with the Dota bot is that in April it was really bad, and then on June it was an amateur, on July it was a semi-pro, on late July it was like a strong pro, and then from July to August it improved very rapidly and then defeated all humans. So I think this is characteristic of self-play systems. I don't think this is the exception, I think this is the rule. Because once you fix all the bugs, once your algorithm is good, you just put more compute and it gets better. And why should it stop once everything is done right? So I think this is what I like about self-play. At least in principle, there is an answer of what do you do after supervised learning? Because supervised learning is kind of boring. You know, you have your data set, you're never going to do better than a data set. So now all we do is data set collection. You want to solve self-driving car? No problem. Self-driving cars, no problem. Just get a huge data set and get 10,000 people to label those images for a few years, and there you go. You got a self-driving car. But that's not inspiring. But with self-play, at least in principle, you can see that, yeah, you put more compute in, and the agents just get better and better. There is another really cool thing. So there is some evidence from evolutionary biology that the reason that we have large brains is so that we could deal with other humans. And in general, it is known that more social animals tend to be more intelligent and have larger relative brain size compared to their less social relative species. And you can also see how this kind of system will produce a lot of social skills, theory of mind, the ability to negotiate, all these things that many attributes that humans have that are uniquely human right now, at least in principle, should naturally emerge from the competitive multi-agent environment. Now, finally, I want to finish with the speculative note. So there is a chance that the final, actually truly generally intelligent systems will be trained in such competitive multi-agent environments. At least it's conceivable. Now, given our earlier observations about the speed of improvement in self-play systems, what we can conclude is that if you accept this controversial statement, then it follows that we should see a very, very rapid increase in the competence of the final agents which will have the general intelligence. And on this uplifting note, I want to thank you for your attention. Any questions? Yes?
I have a question, like, on your agents, when you model a human, like, it ends up always to lift his arms. Is that right?
Repeat the question. Oh yeah, the question is, in the little sumo wrestling video, the agents did lift their arms, and why do they do that? And the answer is that I don't know. Okay.
Your self-play, you ever talk about the stereotypes and low-level policies, something of a generalization to the past. Have you seen something like that, or tried something like that in the self-play environment?
Yes, on the question of, have we tried learning the low-level action, the low primitives in self-play environments? And the answer is, we have not. Yeah, so will it help? Probably. It's still pretty nascent. And one of the big challenges in these self-play environments is how you go about measuring progress. Because, let's say that your agents are doing something